So we constructed at the very beginning of the class a very simple model of the climate of the Earth. And since then, we've been improving it and talking about ways in which it should be more realistic in order to approximate the real world. And so here we started with just original bare rock model of energy coming into and out of a planet, and that determines the planet's temperature. Then we added the greenhouse effect with this plate of glass that absorbs all the infrared light coming from the ground. And then we talked about how the atmosphere, the greenhouse gases in the atmosphere don't absorb all of the light. They absorb only certain parts of the light energy. And there's other frequencies such as the atmospheric window here, which greenhouse gases don't absorb at all. And then in the last unit, we talked about another mechanism of carrying heat around in the atmosphere in addition to the heat fluxes from light, which is convection. And in particular, we found out that moist convection is what drives the thermal structure of our atmosphere. So you have air rising, and it cools and condenses, and that's where it rains, but it dumps latent heat up here and also carries heat around. And so that's sort of where we are. But there's one more thing that the real world has that our conceptual models do not have yet. And that is that the whole world is not a single place. It's not all the same temperature, and the sunlight intensity is not always in balance with the energy going out by infrared locally. So the real geometry is that you have sunlight all coming from one direction, from the sun, and it's coming in most strongly at the equator. Infrared light is leaving everywhere around the Earth, and the rate at which it leaves depends on the temperature of the ground, according to epsilon sigma t to the fourth. And it turns out that if you look at a given location on the Earth, the incoming and outgoing energy budgets do not balance. They only balance for the Earth as a whole on a long enough time average. So here is a plot of the sunlight intensity in watts per square meter as a function of latitude, and it's very strong at the equator. Here is a plot of the infrared energy leaving the Earth as a function of latitude, and it's also stronger near the equator because it is warmer at the equator than it is at the poles. But there is a deficit. It's not hot enough at the equator to drive the energy out as quickly as the sun is bringing it in, and it's not cold enough at the equator, at the high latitudes, for the infrared to be as low as the sunlight coming in. And the difference is what we call heat transport. It's heat being carried by the atmosphere and by the oceans from the low latitudes to the high latitudes. So all of these winds and currents on Earth that have to be simulated with our gridded climate model are heavily impacted by the fact that the Earth is rotating. In fact, you can't even look at a weather map without seeing the effect of Earth's rotation. So we take into account rotation using an idea called the Coriolis acceleration, which is basically a fake. It's a fudge factor, which is intended to account for the fact that the rotation is happening. So to see what's going on, imagine a merry-go-round with two people on it on opposite sides. And if we're looking down on the merry-go-round from a stationary frame, so if we're not rotating but the thing is spinning, you'll see, say, Bob here throw the ball toward Alice, but by the time the ball gets to Alice, she has moved to there, and Bob is now here. And that all makes perfect sense. The ball is going in a straight line just like Newton's laws say it should do. But if we want to spin around with the merry-go-round and still make sense of things, we have to, what we actually see, we don't see Bob or Alice moving anymore, and what we see is the ball that Bob throws, it looks like it curves off to the side. And so we could sort of hack Newton's laws of motion to make the ball do that by adding this fake force, the Coriolis acceleration. It always goes at 90 degrees to the way the thing is moving, because we want this ball to turn. So if the fake force was pointing forward, it would make it go faster, and we don't want that. Or if it was pointing behind it, it would make it slow down, and we don't want that either. So it has to be at 90 degrees. So it's easy to understand the Coriolis acceleration on a merry-go-round because everything is spinning at the same rate on the merry-go-round. But we're on a planet, which is a little more complicated. And the way to visualize the rotation of the Earth, I mean, one really cool way to visualize it is with a device known as a Foucault's pendulum. So they have these at science museums. Usually they have a big atrium because it has to be very tall. They want this thing to get going in the morning and swing all day long. And what happens is, as you're standing there, the Earth is actually rotating under the pendulum. And so a pendulum that's going in one axis at the beginning of the day will be going in a slightly different axis later on in the day. So you can set up a little ring of little dominoes or something, and every 10 minutes it'll knock one over as the Earth is rotating under it. Well, so imagine a Foucault pendulum at the North Pole. That's totally like the merry-go-round. It's no different. The pendulum is going to want to stay in a fixed plane relative to the fixed stars, and the Earth will just spin underneath it. And so what you see is 360 degrees of rotation in 24 hours, the actual rotation rate of the Earth. Now, let's set up a Foucault pendulum at the equator. And we'll get it going north and south. That's the easiest way to visualize this for me anyway. Hopefully it is for you too. So we'll get it going north and south, and it wants to stay in that orientation relative to the fixed stars. So stars up here, stars down there, it's going to keep going north-south as it rotates around. Of course, it'll always be, pointing down toward the center of the planet as it goes around, but it's going to be going north-south, and it's not actually going to feel any rotation at all at the equator. And then if you have a pendulum somewhere in between, you get an amount of rotation, which is sort of in between the full rotation of the planet at the pole and no rotation at the equator. So less than 360 degrees in 24 hours, or one full rotation in more than 24 hours. So the way that physicists visualize this and calculate this is by drawing a line, a vector, a line that has a direction, which is the rotation axis, and so that would be like the North Pole, and then comparing that to a line that points toward the center of the Earth at any latitude, which would be like a flagpole. And the amount of rotation you get is proportional to what they would call the projection of the flagpole on the rotation axis. So at the North Pole, they're both going the same direction, and so you get the full rotation. But as you get to the equator, they're orthogonal to each other, and so actually you get no rotation at the equator. And then the south and the southern hemisphere, the rotation works the same way, but in the opposite direction. So how does the Coriolis acceleration affect flows? It's a really interesting phenomenon known as geostrophic motion. So imagine that you have some sort of a push force. So this could be high pressure on one side of a column of gas and low pressure on the other, or it could be wind blowing over the surface of water and tending to push the water in some direction. So what the water does initially, if you push it in some direction, is it goes in that direction, in the same direction as you push it. And when it starts going in that direction, you arise a Coriolis acceleration, which is always going at 90 degrees to the direction that it's moving. So what this is acting to do is pull the direction of the flow around, to rotate it the same way as the direction of the ball in the merry-go-round was deflected by the Coriolis acceleration. So after a little while, the flow is not going the same direction as you're pushing it anymore. It's sort of rotated off to the side, and the Coriolis is always following the flow here. And eventually, you end up with the equilibrium state, which is what it sort of relaxes to and then stops changing. So it can stay in this equilibrium state forever, where the flow is actually astonishingly going at 90 degrees to the side of the way you're actually pushing it. And in this way, the Coriolis, which is 90 degrees then to the flow, is now pushing back, exactly counteracting the push force. And so that's why this is equilibrium, because those forces can cancel each other out. You can't even look at a weather map without seeing the effect of geostrophic motion. So a hurricane is basically a hole in the atmosphere where the pressure is lower, the atmospheric pressure, than it is in the surrounding air. So you remember that the pressure is just the result of the weight of the air on top of your head in the atmosphere. And so this low pressure at the ground in the center of a hurricane just means that there's less air piled up there. And the difference in the air pressure is leading to a push force going from high pressure to low pressure. So you would think in a non-rotating frame, if you had higher pressure of gas here and lower pressure there, it would just go from the high pressure to the low pressure and fill in the hole. But due to the geostrophic motion, you have the flow in the atmosphere is going at 90 degrees to the way you're pushing it. It's going around like this, and then where the flow is going in this direction, the Coriolis is pointing at 90 degrees to that, and so the Coriolis is reaching this state of equilibrium where it's pushing back against the push force in the geostrophic equilibrium. So it is as if you made sort of a hillside or a dip in a membrane or something like that, and you set a marble on it, and in a non-rotating frame, it would just roll to the bottom of the hill. But in a rotating frame, it doesn't go the way you're pushing it. It goes sideways to it, and so it goes around and around and around. Only very slowly does it go down. And this is why hurricanes last as long as they do. There's also a feature on Jupiter called the Great Red Spot, which, as far as we know, has been there for centuries. And it's just one of these sorts of systems with a pressure imbalance and the flow going around and around and around in geostrophic motion. And that's why it can last for so long. You also see the effect of geostrophic motion in ocean flow. So the Gulf Stream is a giant river of water in the North Atlantic. And actually, the sea level is about 1 meter higher on one side of the Gulf Stream than it is on the other, which it's very wide feature, so you never see a wall of water a meter high. It's too spread out to be that obvious, but you can measure it. And if you measure also the pressure at some level underneath the ocean level, you have higher pressure here where the sea level is higher because you have more stuff over your head than you do here where the sea level is lower. So you have a pushing force going in this direction, and then in geostrophic motion, you have the Gulf Stream, which is an arrow going into the board here at 90 degrees to the direction that you're pushing it. So in order to simulate the way that the atmosphere and the ocean carry heat from the low latitudes to the high latitudes, we have to understand about how flow occurs on a rotating sphere. So in order to simulate the climate, we have to simulate the processes by which this heat gets carried from the equator to the pole. We have to simulate the weather. And this is hard because of a phenomenon known as the turbulent cascade. So we're sort of stirring this, or we're driving this with a planetary size forcing. The difference between the energy coming in and out at the equator versus the pole, that's a difference that's as big as the planet. But the flow that results from that is not as simple as these nice planet-size arrows that I drew. The flow tends to break up large eddies, large motions tend to break up and make smaller motions. It's called the turbulent cascade. So a planetary-sized forcing leads to large-scale motions, which then break up until finally they are the size of the storm systems that affect us from hour to hour in the weather. And so this is where climate science starts to get hard. We simulate the climate of the Earth and all of these motions, all of this weather, on a grid, like a checkerboard in a computer program called a climate model. So the surface of the Earth is represented by this grid, and maybe you have values for the pressure and the temperature in the centers of these grid points, and maybe you calculate what the winds should be, the flows, in the cells, the cell walls between these grid points. The problem is that we would like to have as much detail as we can have in our simulations of the weather so we can get things right. We want to have enough grid points so that we can adequately see, so that the model can adequately express the smallest scales of the turbulent cascade. And the problem is that if we decide to double the amount of detail in a model, for example, that would mean having twice as many grid points in the horizontal and twice as many grid points in the latitude, longitude, and then also in the vertical, having twice as many grid points. And so, and then the model steps forward in time, and if we make these boxes smaller, it turns out that we have to take smaller steps in time. So a normal climate model might take a time step of 20 minutes, for example. And if we made it twice as many grid points, maybe we could only take 10 minutes per time step. So we'd have to take twice as many steps to do a day or a year or something like that. So it turns out it's a very steep computational curve. If we want to double the amount of detail, we have to do 16 times more math. And so it gets much, much harder and much, much slower. Computers are getting faster, but climate scientists are going to leave the computer room hungry for a very, very long time.